So, we will talk about time dependent perturbation theory, and to distinguish it from the time independent perturbation theory that we have seen in details. Here, in addition to a removal of degeneracy, either partial or complete removal of degeneracy, here one can also get transition from one state to another. So, in addition to removal of degeneracy, there could be transitions, and this transition is purely facilitated by the time dependent term in the Hamiltonian. And so, we will start with the formalism part, and then we will talk about the harmonic perturbation, that is harmonic in time. We will see how these transition probabilities are from one state to another. In particular, we will talk about a two level system, and in that connection the spontaneous and stimulated emissions and absorptions as well. And we will draw a parallel with lasers, where we talk about the Einstein's A-B coefficients. All right. So, let us start with this formalism part, and the formalism is that we now have a time dependent Hamiltonian, or rather the perturbation term is time dependent, and we have learned it earlier that psi of t, rather we have this the time independent problem is that you have a psi which can be expanded in terms of this C n and phi n, where phi n is the basis and C n are the complex coefficients. Now, when you go to the time dependent problems, the basis remains the same, but what you do is that you introduce a time dependence in the C n's. So, this is what we have done, and we have said that this is most convenient not to change the basis, because every time then at each time there will be a new basis, which is not a convenient model to work with. So, we will keep the basis to be same, and there will be a C n of t, and this can be written as C n at time t equal to 0 exponential minus E n t over h cross, and we also have phi n. Okay. So, these was the stationary state ansatz, and then we let us call this as equation 1. Okay. So, the time dependence, as I said, is carried on by these coefficients, and that is how this time evolution of the state psi of t proceeds. So, we know that this problem is known, that is h 0 phi n. This is equal to E n 0 phi n, that is the unperturbed problem. So, this problem is known, okay, and this known problem, let us call it as 2, and so we have to solve this equation, which is I h cross d d t of psi of t, and now this is equal to h psi of t, and say this psi can be split into a time dependent, a time independent part, which is the unperturbed part of the Hamiltonian, and say there is a lambda h prime t, which is explicitly dependent on time. So, we can put it into the Hamiltonian, and we have this d d t of psi of t. This is equal to h 0 plus lambda h prime of t and psi of t. Okay. So, now we have a time dependent problem to solve, and the solutions will have to be done carefully, and we will still take the same ansatz that we have taken, that is this ansatz equation 1. So, if you take this ansatz and convert this equation to an equation for C n t instead of psi t. So, convert this into an equation for C n t, okay, and which is same as the Schrodinger equation, is just rewritten in that form, and that can be done when you so you have a summation over n and I h cross d C n d t and a plus E n 0 C n t. E n 0 is the, as we said, that this is the eigenvalue of this unperturbed problem, which is known. So, it is En0 psi Cn of t and this into exponential minus I En0 t over h cross, and then there is a phi n, and this is equal to En0 again and plus a lambda h prime of t and Cn of t exponential minus I En0 t over h cross and phi n. So, this is nothing but the Schrodinger equation expressed in terms of, not in terms of psi of t, but the coefficient Cn of t is just the analogous of the Schrodinger equation. So, what you can do is that you can take a scalar product with some phi m and cancel this exponential minus I E m 0 t by h cross. Why I E m? Because you take an overlap with this bra phi m, and when you do that, this phi m phi n will give you a delta m n, and then you have this exponential minus I E m 0 t by h cross, and that can cancel from both sides, giving you this equation. Now, because of these Kronecker delta that you come in, when you have a phi m phi n, this is equal to a delta m n, and then there is a sum over n. So, the sum really goes away, and you have a term which is like a dCm dt, which will write it as a Cm dot. Okay. So, you get a dCm dt, which is nothing but Cm dot, which is equal to a lambda and Cnt exponential I E n 0 rather E m 0 minus E n 0 t over h cross, and then you have to take the overlap of this phi m, I mean the h prime in between the phi m and the phi n, which are the eigenstates of the problem. So, this is the equation that we wanted to get at, and this equation is I mean we are really doing first order in lambda. So, lambda can be dropped because we just put that lambda to expand the perturbation Hamiltonian, but it was very clear that we are doing a first order perturbation theory, because we have kept this term lambda, linear term in lambda. So, this lambda can be eliminated, and one can write this equation it is equal to I h cross C m dot. So, do not miss this dot, because this C m dot is equal to d C m dt. Okay. So, make sure that the dot is put bold such that one does not miss it, and I drop this lambda for now, and then we have a n, and then there is a C n t, and we will write it as exponential I omega m n t, and then we have this matrix element of h prime between the basis states of h 0. Okay. So, this is an important equation which needs to be solved in order to solve for the time dependent problem. It has all information, it has information about the h prime that needs to be taken into account. So, in the first order, in the perturbation term, what you get is that the wave function has an evolution that is given by this equation, and this equation, even though you do not see a psi of t here, but it is exactly this carries the same information as psi of t in terms of this complex coefficients, which are C m dot of t, which is equal to sum over n, and these coefficients and the matrix element of h prime between the eigenstates of h 0, and then there is this omega m n. So, this omega m n is nothing but E m 0 E n 0, which are two unperturbed energies, and divided by this h cross. So, you see that these h cross is absorbed in the step above, and E m 0 minus E n 0 divided by h cross becomes omega m n. And this has a solution. So, it is like d C m dt and then one can actually write down an integral solution for this. Because we are now doing this problem in the first order perturbation theory, we will simply put sort of index 1. So, we will write this as CM1, okay, because this 1 would simply indicate that we are really doing a first order perturbation theory, and in sort of all practical purposes we do not need to go beyond that. But however, in some situations where the first order correction or the splitting or the transitions for some selection rules go to 0, then one may have to go to second order, but we really do not go into that. So, your CM1 T, the solution of this equation, is nothing but 1 by I H cross, the I H cross goes away, and now I have these H prime M K T prime and exponential I omega M n T prime and d t prime. You see, what we have done is that we can of course, we can write it M n, there is no problem. I mean, so it was just a dummy variable. So, now this integral, let us say, is from 0 to some t 0. Okay. So, what is h prime m n? So, you have a phi m h prime phi n, which is nothing but equal to h prime m n. So, that is a matrix elements between these eigenstates m n n. This exponential term was always there, and what you have done is that you have integrated this equation in order to find Cm, and as I said that we have intentionally suddenly have brought in this superscript 1 within bracket just to make sure that we are doing a first order perturbation theory. And very important thing is that the perturbation is switched on from 0 to t 0. So, h prime is switched on, that is you apply this perturbation between some initial time which can be 0 or it can be even infinity, I mean minus infinity, so that it is switched on at very large negative times, and then it is only switched on till certain time. So, this 0 to t 0 is makes sense. So, that is the one that we have in this particular case. Okay. All right. So, this is the equation that we need to worry about, and how these equation can be used. So, basically if you really think about this, that this equation really gives you this the Cm 1 square gives you this mod square of this, it gives you a transition probability from some initial state n to some final state m. Okay. So, these are the states that are represented by the kets. Okay. So, and we will have to calculate that. All right. So, let us sort of specialize it for a particular case, so that we can apply this formalism that we have learned. And so, what we do is that we can write down this h prime m n is equal to some a m k. Let us not worry about this a m k to be that is the space part of this matrix element of H. So, that space part would of course lift the degeneracy, and that is what we have handled in the time independent perturbation theory. Now, we are talking about the time dependent one. So, we will only talk about harmonic terms, say for example like this. So, this is an example of, so that we can apply the first order perturbation, time dependent perturbation theory that we have learned. Okay. So, this is your H prime m, and sorry, this has to be n, and so a m n some matrix element which a m n is of course phi m H prime phi n, but only the space part. Okay, so this is we start with that. So, we have a CM1 T, the one that we have written it down, and we can take this n state to be equal to the original state. So, let us just say that your n state is a ground state. Okay. So, this is n is equal to 0 say. So, you assume that your it is a ground state of the system, and then what you have is that it is a 1 over I h cross a m n and 0 to t 0 d t prime and exponential I omega m n and t prime, and what we do is that we replace this sign by its exponential forms, which are exponential I omega t prime minus exponential. See, why am I writing t prime is that you are putting it inside an integral, and so we use a dummy variable so that we can integrate it from 0 to t, or here we are talking about 0 to t 0. So, it is a dummy variable that needs to be integrated over, and that is why we are not using t, but they mean the same thing. So, it is exponential minus omega I omega t prime and divided by 2 I, and that is the basically the sin omega t part, where we have used the sin theta is equal to exponential I theta minus exponential minus I theta divided by 2. Okay, 2 I, sorry. Okay. Because your exponential I theta is cos theta plus I sin theta. Anyway, so that is the thing that you have, and when you do this integral, you have a m n and with minus 2 h cross, and then you have a 0 to t 0, and we have a d t prime, and we have exponential I omega plus omega m n and minus this d prime, and exponential I, well, I mean this can be written as in the reverse way such that there is a symmetry, and omega, and this is like omega m n minus omega and so on. So, that is the term that we have, and we can integrate this, and what we get is this I a m n divided by 2 h cross, and we have exponential I t naught, and we have omega m n plus omega divided by omega m n plus omega minus exponential I t 0 omega m n minus omega minus, so there is a minus 1 here, and then there is another minus 1 here, and then we have omega m n minus omega and this. So, what we have done is that we have simply integrated this, and exponential integration is very simple, and then you get this energy denominators appearing there. Okay. So, we can measure the probability of transition from some initial state, and you can take this initial state to be any state. Okay. So, it can be a ground state, and we have not used it, but we have kept it n to be the initial state. So, this is the initial state, and m is the final state. So, like these are two states, and this is n and this is m, and these mod square of the CM1 will give you a transition probability from some initial state, that is n, to a final state, that is m. Okay. So, these transitions are of course new for us because we have not seen them in the time independent perturbation theory. Let us look at these denominators, and these denominators will tell us something. So, let us so inside the bracket. So, denominator of the first term. And so, we have what happens when the denominator goes to 0, that is like the term blows up. So, if omega mn plus omega goes to 0, then what we have is that E m minus E n divided by h cross plus omega equal to 0. And why we are looking at this blowing up of this term or this denominator goes to 0, because this omega is a variable frequency. That variable frequency is associated with the perturbation term. So, if the perturbation actually clicks, or rather it resonates with the energy difference between the two states that we are considering, then there could be a transition, because that is going to give you the largest transition probability. So, if you tune your omega, the omega that you are applying as a perturbation which is equal to the difference between the two energies, then of course, you have a sort of large that ratio becomes very large, because your this thing goes to 0, your denominator goes to 0, and there is the transition probability is going to be very large, and that is what we want to see. So, this means that your E m, this equal to E n minus h cross omega, and so of course, this means that E m is less than E n. So, that tells you that basically your H m n, the perturbation term, it takes away energy. And when it takes away energy, it is called as a absorption. Okay. And if you look at the denominator of the second term, and when it diverges basically, so you have a omega mn minus omega, that is equal to 0, and that gives you finally a em equal to En plus h cross omega. So, your final state has energy larger than the initial state, and this is called as the emission. So, emission is coming down from higher state to lower state, or rather m is greater than n, and the reverse actually happens when you have absorption. So, this picture that we have this is only for the emission part, and when you have the absorption, then you have these lying above this thing, that is also possible. So, your this the two terms actually have both these possibilities. Okay. And so, we will mainly be interested in this emission term, but at the same footing the absorption term can also be considered. So, let us look at the second term and see what happens. So, we are interested in the second term, which means that we talk about the conventional picture where E m is greater than E n, and we are going to talk about the emission spectrum. So, this is equal to minus I a m n divided by 2 h cross, and rewriting it again, it is I t 0 omega m n minus omega minus 1 divided by omega m n minus omega. Okay. So, this is the term that we have, and we can do just a little bit of mathematical manipulation, and can write it as a m n divided by h cross, and we have this exponential. So, what I do is that we take out this exponential, and or rather we take out half of this exponential such that we can write it in a symmetric fashion. So, this is what I take a common here. So, it is exponential I t 0 by 2 omega m n minus omega. This, if it is taken as common, then we can write it. So, basically there is a minus I there, and then there is a 2 h cross there, which will cancel out because there is a 2 I there, and a sign of these T 0 and omega m n minus omega and this divided by omega m n minus omega and so on. Okay. So, these two terms, now this 2 will cancel with 2 and this minus I will cancel with I, and we are left with these terms, which is a m n by h, this half I T 0 by 2 omega m n minus omega, and this sine term which is there. So, this is your that C m 1 term only for the emission. So, the second term of C m 1 t, and what we want is that we want to take the mod square of that to get the transition probability, and this is equal to a m n mod square by h cross mod square. This term will not be there because you are taking a mod square. So, this is exponential I and there will be exponential minus I coming from the C star and will not give you anything, and then finally, we have a sine square. Now, writing this, let me just write this as alpha, and we have an alpha T 0 by 2 and divided by some alpha square. Okay. So, you can write this beta equal to alpha T 0 by 2. So, you can write a beta equal to some alpha T 0 by 2. Anyway, these are constants. I mean, alpha is these omega m n minus omega, in the sense that for a given frequency of the perturbation, of course, omega is constant, omega m n is constant, and so on. So, we have a form which is the transition probability for emission or the emission probability, but we are just trying to simplify it so that we can bring it to a form that's we can interpret the result. Okay. So, use this beta there, and what we have is that we have a C m 1 t square, only the emission part, it is equal to a m n by h cross mod square of that sine square beta divided by beta square, and a constant which is coming because of this alpha to beta transformation, which is t square by 4, and anyway that is a constant. So, what is important for us is this term sine square beta by beta square. This is called as a sinc function. Okay. It is like a sine x by x square of that. So, it is like sine square x by x square, and you can actually plot this function. I will draw a freehand plot, but you can do it in computer, and it will be like there will be a central peak which is maximum, and then the subsequent peaks will be smaller and smaller and smaller and so on. Okay. So, well, it is symmetric. Do not mind too much about this details of the drawing, but it is of course symmetric. So, this is your C m 1 t square mod square of that is being plotted, and this is as a function of alpha, which is nothing but omega m n minus omega. Okay. So, that is been plotted as a function of that, and of course, you can also call it as it is a basically. So, what we plot is that sine square beta by beta square. Okay. And this peak value is equal to a m n by h cross square into t square by 4. That is when the sine square beta by beta square equal to 1, and this will happen at the 0 will happen at 2 pi over t 0. So, this is alpha equal to 0, and this will happen at this is like 3 pi over t 0, and we have 4 pi over t 0, and symmetrically on the other side as well, and all these are like 5 pi over t 0. This is in terms of alpha. So, pi over T 0, that corresponds to a value which is A m n by h cross square, and T 0 square over pi square, okay. T 0 square over 4, sorry, not pi square, that is 4. And similarly, the 3 pi by T 0, this will be this term, and divided by 9, this whole thing divided by 9, and 5 pi by T 0 will correspond to this whole thing. I mean, so let us call this quantity to be equal to say x, say. So, this x by 9 and x by 25 and so on and so forth. Okay. So, these are the values that it goes down as you go away from the central maxima. Okay. So, the physically it means that if your perturbation term has a frequency that matches exactly with the level spacing, the energy difference between the two levels, then there is a large emission probability that is there for alpha equal to 0, which corresponds to omega m n equal to omega. As you go to go away on either of the sides, that is, you make omega to be larger or omega to be smaller, you see that the intensity of this emission spectrum, or the probability of emission, goes down very quickly. At times 2 pi by T 0, it just has a 0. So, there is no emission that is going to happen, that happens because of the sine square beta by beta square. And at 3 pi by T 0, it has a value which is 1/9 of the value that you see at alpha equal to 0, and then it becomes 1/25 of the value that you see at these alpha equal to 0 at 5 pi by T 0 and so on and so forth. So, this tells you conclusively that it really goes down quickly and so on. All right. So, this is what in a nutshell what perturbation theory is, and we can write down rather get a little closer to what the experimentalist would do or would like you to do, because this is just a transition probability. It has to be multiplied by the energy density of radiation and speed of light and various things in order to actually transform it into intensity, because the intensity of light is what you measure in experiment, or rather you see that on the screen or on a spectrograph. So, that is an important quantity, and this can be actually one can get a sort of one-to-one correspondence if you think that. So, once we get this intensity of these or rather this transition probability for this this radiation, or rather this emission transition, then the intensity of EM wave this is given by I equal to half epsilon 0 c. Epsilon 0 is the permittivity of free space, and some E 0 square, which is associated with the electric field, and c is the speed of light. So, if you want to write this as say Cm1 T, this can be written in terms of all these quantities, which are say half and then you have this Amn mod square, and these I divided by epsilon 0 c h cross square, and these sine square. I will simply write it as sine square beta by beta square. Now, with this T 0 square over 4. So, this is the same thing written in terms of the intensity and so on. So, this intensity can be replaced by the speed of light and the these radiation energy density of radiation. So, this quantity is nothing but the energy density of radiation between a frequency omega and omega plus d omega. Okay, so this transition probability finally brings me to this thing. Let's call it as gamma mn. You can write it as 2 epsilon 0 c h cross square, and we have this a mn square, and it's actually average of that, sort of this average is required to have these overall frequencies, all available frequencies, so that you have this u omega and then this sine square. I will not open this thing, I will still write it as sine square beta by beta square, and we have this T 0 square by 4 that is coming in, that can be pulled out, and then we have this d omega, and this is over all frequencies, I mean 0 to infinity. Okay. So, that is really the transition probability, but nevertheless, I mean if you do not want to do these transformations, your CM1 theoretically still conveys the same meaning, apart from certain constants that you see appearing because of this, all these transformations from one sort of variable to another, where we brought in the intensity, and then this intensity was later on written as in terms of the energy density and so on and so forth. Okay. So, let us go back and do a simpler problem, and the simpler problem is just a 2 level problem, where instead of Mn we will simply talk about 1 and 2 rather. Okay. So, let us see that what that comes. So, time dependent perturbation theory for 2 level problem. So, we will call it time dependent perturbation theory TDPT for 2 level systems. Okay. So, let us say these levels are psi A and psi B, they were labeled as M and N, but now we just talk about a psi A and psi B. So, the C is equal to C A psi A plus some C B psi B, and of course, these C A and C B are dependent on time for these time dependent cases. So, psi of t is nothing but C A exponential minus I A 0 t over h cross psi of A plus a C B exponential minus E B 0 by t by h cross psi of B. Okay. So, that is the time dependent thing, and we of course know that h 0 psi A, this is equal to E A 0 psi A and h 0 psi B, which are the unperturbed eigenstates of the problem, E B 0 psi B with well defined energies E 0 B and E 0 A. And these well defined energies help us to build up the wave function at subsequent times, and we can now we need to find C A t and C B t. And what you do is that if you put these ansatz into the Schrodinger equation, so let us call this ansatz as 1. So, put this ansatz in h psi equal to I h cross del psi del t or d psi dt. What you get is that you get because you have 2 terms that you need to your psi of t, there is a function of t which I left. So, when you take a derivative for the right hand side to be calculated, the derivative will involve 2 terms, both are dependent on t. So, you have to apply the chain rule by taking a derivative of one, keeping the other to be constant, and then repeat the thing with in the reversed order. So, what you get is that you get 2 coupled equations, and these 2 coupled equations will tell you that so if you see that there is some cancellation. I will not repeat some really trivial steps here, you can do it. I hope you understand what has been told. So, you have this h which has to be operated on psi. So, you write h of psi, this psi, and the right hand side requires you to take a time derivative, and while taking the time derivative of these underbraced terms, there are two terms and some of them will cancel, and you will have a C A dot T, that is the equation of motion for C A, which is nothing but the Schrodinger equation, is equal to minus I by H cross C A H prime A A. Now, the C A means really that you have C A at 0. Okay. And then the C B, or let us not specify this. So, this is C B and H prime A B and exponential minus I E B minus E A by T by H cross, and the other term will become equal to C B dot T. This is equal to minus I by H cross C B H prime B B C A H prime A B exponential minus I E A minus E B T by H cross, and those are the two coupled equations that you need to solve. See, this is important because the time derivative of C A requires the knowledge of C A and C B at time t equal to 0, and same that C B dot also requires the time evolution of, or rather the the knowledge about C B and C A at time t equal to 0, and these energy terms are there which are between, like the energy differences. Okay. Now, it is almost natural to assume that, or it is easy to understand as well, that the perturbation term will not have any matrix elements between the same states. So, these terms which connect the state to itself by H prime, that is not going to happen because your H prime is explicitly dependent on time. So, this term will have a time, means there is a omega associated with it, there is a frequency associated with it. So, these terms only will have matrix elements with the other state, that is A will have matrix element with B and B will have matrix element with A, but these terms are usually equal to 0. So, there is no matrix element of H prime between the diagonal states or between the same states. Okay. So, this is equal to 0. That of course simplifies this equation or the set of equations. It is like a C A dot T, this is equal to a minus I over H cross C B H prime A B exponential minus I E B minus E A T by H cross, and also you have a C B dot which is equal to minus I over H cross C A H prime B A exponential minus I E A minus E B T over H cross. Okay. So, it simplifies the equation that there is no diagonal elements and it is only the off diagonal elements, nevertheless it is coupled basically. So, if at t equal to 0 the system starts from the state A, which means at t equal to 0, say this is for an example. So, at t equal to 0 you have the system starts from psi A, that means its C A 0 is equal to 1 and C B 0 equal to 0. Okay. Now, at time t, say the system is found in this. So, this psi b will if it is found in psi b, then it is equal to C b equal to C b at time t equal to 1 and C b at time C a at time t equal to 0. Okay. So, that it tells you that the system has made the transition from one state to another, and if you are talking about the emission, then A is a lower state, lower energy state, and other one, that is B, is a higher energy state. Okay. So, we need to kind of put these things in perspective, and let us talk about this Einstein's AB coefficients and see that how all these things that we have learned from the first order time dependent perturbation theory and how it can be applied to these properties of laser. So, we will do a semi classical picture and we will introduce these Einstein's coefficients. And we have this as a picture. So, we have this state as state 1 and this state as 2, or you can call it A B, whatever you want to call it. And let me now use color. So, let us use 3 colors for example. So, there is a maroon color we have done. So, let us call that as A21. We will tell you what A21 is. These are these MNs. So, because we are talking about 2 and 1. So, this is called as the the emission. This is one of the emissions. We will define it as spontaneous or stimulated. So, let us use another color. Let us use this say for example blue, and this blue color would correspond to a B12 or so sorry, this is 812 because this is defined as A12. We will do that in just a while. So, A12, and let us choose another color, maybe a green one, where we show it. So, this is a B21. Okay. So, let us just define them now. So, these A's are A and B are Einstein's AB coefficients. These are called A and B coefficients. I repeat this A and B twice, but they the ones that we are using are called as the Einstein's AB coefficient. So, A coefficient stands for spontaneous emission. So, it spontaneously emit from, and when you write it like this, it actually means that A12. So, the target state or the final state is written first and the initial state is written later. Okay. And B coefficient actually they are induced emission or absorption. Okay, so the transition probability for spontaneous emission is so this is per unit time basically. This is equal to A12, and transition probabilities for induced emission again per unit time. This is equal to B12, but it also depends upon the energy density of radiation. So, we write it as B12 omega. So, transition probability for induced absorption per unit time, this absorption, and this is equal to B21 U omega. Okay. So, at a steady state, when all these upward and downward transitions are equal, that is no more transition is happening. So, at steady state, you have N2, which is the occupancy of atoms in the state 2, that multiplied by A12 plus B12 u omega, this is equal to u omega, as we have said that it is the energy density of radiation, is equal to N1 B21 u omega. Okay. So, if you do this, if you just open this bracket, so it is A12 plus B12 u omega, this is equal to N1 by N2 B21 u omega, and so your E2 minus E1 is basically the perturbation term, which is basically the frequency of the perturbation. So, H cross omega. Now, we also know from Boltzmann statistics that N1 by N2 is nothing but exponential of E2 minus E1 divided by kT. So, the occupancies of these two states at a temperature T would be given by this, which is nothing but exponential H cross omega by kT. So, this ratio that you got here N1 by N2 at a temperature T is nothing but this exponential H cross omega by T. So, basically the transition rate that you get here is that so minus dN2 by N2, it is like a beta T, which is like a radioactive decay with inverse of beta as the lifetime and so on. So, that tells us that if you want to have a one-to-one correspondence and using the steady state equation, if you want to calculate the this u omega, then the u omega would look like so B12 u omega, this is equal to exponential H cross omega by kT B21 u omega, and so u omega, this is equal to A12 divided by exponential H cross omega by kT into B21 minus B12 and so on. So, that is the energy density of radiation, and if you compare with the Planck's formula for the radiation this energy density, then it looks like this H cross omega square by pi square c cube and divided by e to the power H cross omega by kT minus 1. So, this is Planck's law or Planck's law of black body radiation. So, you see that it is very easy to see that this B2 and B12 is same as B21. To remind you that B12 and B21 are these things which we have said here. So, this B12 and 21 are these transition probability for induced emission and induced absorption. So, they are same, and not only that, your A12 by B12 from this comparison gives you H cross omega cube divided by pi square c cube. That tells you that A12 is equal to H cross omega cube by pi square c cube into B12. So, there are three coefficients and there are two relations that you have. One relation is that two of them are exactly same, and the other relation is that the third one, that is A12, has a relationship with either B12 or B21 which are same, which means that there is one really one independent Einstein coefficient. So, we have calculated the transition probability, the CM1 square, and then have gone ahead and said simplified it for just a two level problem, and then these transition probabilities have shown to have a sharply peaked structure at resonance, and as you move away from resonance, the probability of transition or the transition probability drastically goes down, and then using a semi-classical picture we have calculated the Einstein's coefficients from the energy density, comparing it with the energy density of the black body radiation. And this sort of concludes, of course, we have not done any example problems which will be dealt with in the assignments or the tutorials. And so, we have introduced this time dependent perturbation theory and have explained how, in addition to removal of degeneracy, which was already done by the that space part or the spatial part of the perturbation, this causes transitions between one state to another, and that is an important thing. I mean, and these are related to the lasing action, where there are the atoms are being either pulled up from one lower state to a higher state, which are induced absorption, or there could be two other processes which are spontaneous emission and induced emission. These coefficients can be calculated from all the CM1 square mod square that we have started with, and we have told how for a harmonic perturbation these transition probabilities look like. So, we will stop here, and we will continue with some more things, particularly these what are called as a Klebsch-Gordon coefficients, etc. That needs to be done and explained. That is a little complicated if one has not done it before, but I hope I will be able to explain that how it works. Okay. Thank you.